Hello, everybody. My name is Ron. I'm from Israel, and I lead the developer relation out in Google Tel Aviv. And today I'm going to talk to you about battery and how we can be more efficient in that matter. But first, I would like to make a quick poll. Looks familiar? Anybody use this? Raise your hand. Okay. What about this code snippet? Anybody wrote something similar to this? Opening HTTP connection, fetching some website. Raise your hand, guys. Okay, let's do it this way. Anybody didn't write something like that? Get out. Anyway. Okay, so you must be asking yourself, hey, everybody's doing it. What's the big deal here? Why we've got this weird guy talking? Accessing the network, fetching some data over the internet is commodity. Everybody's doing it. What's the big story here? Well, it turns out that accessing the network, like opening HTTP connection, or especially on cellular networks, it has a significant impact on battery life. In fact, that's the #1 battery killer today. If you would check and see what apps are doing, what's killing your battery, what apps are actually doing on your phone that kills your battery, it won't be GPS, it won't be the screen, it will be network. Okay? It's true, GPS is a pretty good battery hogger, but most of the time it's off. While accessing the network, apps are always accessing the network. And today we're going to fix it. And if you still ask yourself why we should care about battery life, I can share with you research that we've done in Google. It took us years to conduct this research, and we learned that when the phone is dead, there's no battery, the phone is dead, the user is less likely to use any app. Yours as well. Okay, so you may want to keep the phone running a little longer. So the first thing that we'll do, we will try to understand how things are working under the scene, behind the scene, under the hood, how cellular networks are actually working. So, turns out that wireless phone, like this one, are actually wireless. There's no cable here, right? We rely on radio transmission, radio communication back and forth from my cell phone to a cell tower to a base station, which is located out there. It means that inside the phone there's a little chipset with radio transmitter and receiver that transmits radio frequency, radio communication to the base station, which receives that communication, process it, and send some stuff back. Now, every communication, every time we want to send something, we need frequency. We use frequency. And frequency is expensive because frequency is limited. It's a physical resource. It's not like IP. We're running out of IP addresses. Let's make IPv6, and suddenly we have more. It's a physical thing. It's a physical limitation. Think of this room. There's only so much space inside this room. I cannot put 1 million people inside this room, just not enough space. Same thing with frequency. We don't have enough frequency. And actually, the cell tower cannot speak and communicate and talk and allocate frequency to 100% of its clients 100% of the time. Simply doesn't make it. So instead, the cell tower, at any given moment, decides which clients, which customers, which cell phones will get frequency. He allocates frequency dynamically over time to different clients, to different subscribers, and this way they communicate. Just to give you a rough idea, we're all here in this convention. We're probably all registered with a cell tower, which, I don't know, about half a mile away, and typical cell here in this area will serve, I don't know, about 2,000 people, 2,000 cell phones. But it can only talk to 8 or 12, depends on the technology. In modern country, actually, it's 16, but in United States is kind of falling behind when it comes to cell networks. So over the years, different technologies have emerged to optimize specifically that, to make the allocation process much faster, more efficient, basically to get more bits per hertz. We're talking about HSDPA, HSUPA, what you guys probably know as the 3.5, 3.75 generation, or OFDM and OFDMA, which is LTE or 4G. This is how the radio state machine inside any cell phone in this room looks like. This is what happens when we want to make a transmission, when we want to send a bit over the internet. Now, it's a pretty self-explanatory diagram. Okay, so we can move forward. I see this guy here with a question mark above his head. Oh, no. Okay, I made a simplified version. Okay, let's think that we have 3 states. The first one is idle. In idle, our radio has 0 throughput, no frequencies allocated to it. We can't transmit even 1 single bit. But we're hardly using the battery, we're hardly using any power, only 2 milliamps, which is practically nothing. Now, if the user opens an app and that app wants to send something to the internet and receive something, we need to move from idle to DCH. DCH stands for dedicated channel. In this mode, the base station actually allocates frequency to the client, to the cell phone, in a constant manner, in a periodic interval, like clockwork, allocates frequency. In that mode, again, to make things easier to digest, we have high throughput, but we actually consume a lot of power. Now, let's say we're getting that frequency and we transmitted whatever we needed to transmit, and now the cell phone doesn't need that much bandwidth. The network understands that, and the base station tells the cell phone, hey, move from DCH to FACH. FACH stands for forward access channel. Frequency is still being allocated to the cell phone, but not like before, not like clockwork, but every once in a while we get frequency and we'll be able to transmit and receive. In other words, again, just to make it schematics, let's say that we've got half of the bandwidth and we're using half of the power. We're running in this mode until we don't need, we're done with the network, we don't need the network anymore, and then the cell tower will tell us, hey, move back to idle, where you actually, you're not consuming any frequency, and that frequency can be allocated elsewhere. Now, those transitions, actually, they don't happen right away. They take time. It takes about 2 seconds to move from idle to DCH. Think about it. User opens your app. Your app wants to fetch something from the internet. The user actually waits about 2 seconds before you are able to send the very first bit. And it happens a lot. Furthermore, in DCH, it takes the network some time to understand that this specific client that we're allocating frequency to it doesn't need that bandwidth. He's not using it. Okay? About 8 to 10 seconds, depends on the configuration of the network. And same goes with FACH. Now, those tail times, that's basically frequency that has been allocated and nobody needs it. Nobody's actually using it. That's waste of frequency, which is a huge problem to the AT&T Verizons of the world. But we need to remember another thing. In cellular network, there is no such thing as being quiet, which means that if a frequency has been allocated, you must transmit something. I got a cell phone, moved to DCH, did whatever transaction it needed to do, got the frequency. Now the cell phone doesn't have the app, doesn't have nothing to transmit, but the base station still allocates frequency to that phone. That phone has to transmit something. What do we transmit? Random bits, zeros and ones. We have to transmit something. There are a lot of reasons why to do that. I'm not gonna go into it right now. If you want, you can ask me afterwards. But the bottom line that we understand now that those tail times from DCH to FACH and from FACH to idle, this is pure energy that goes to /dev/null. Okay, that's energy that we just throw away. We're transmitting something. Transmitting something is very expensive, battery-wise, and it just goes away. So now that we understand how those networks operate, we can ask ourselves, what does it mean to us as developers? And at the end, it all boils down to 2 main things that we, as developers, need to focus on. Less radio, less data. Okay? That's what we're going to talk about today. First thing, I want to go over some common mistakes that we've seen lots of people in lots of apps doing, and it's time to put that to an end. First thing, periodic traffic. Now we're used to do priority traffic. Let's say we want to upload analytics or do location updates or just keep alive, okay? Sending heartbeat messages back and forth to notify the server that we're still alive. Here is a use case from a music streaming app that we've looked at. This is a screenshot from a tool called Aero that was developed in AT&T when I was there. I'm going to show that tool later. I'm going to elaborate on it a little more. And as you can see, basically what this tool does, it looks at the network request and it analyzes what the radio state was. And as you can see, the music file in that music streaming app was downloaded as one big chunk at the beginning. Okay, you can see we're in DCH and we're good. But then every 62 seconds, the app actually sent about a payload which is about 2 kilobytes of data to the server, analytics. What is the song, the volume, what the user did, where foreground, where background, stuff that they wanted to know. And every peak here, every 62 seconds, we actually moved the radio from idle to DCH, FSCH, and back to idle. That's a lot of energy that was wasted. How much is a lot? Turns out that 0.2% of their data actually consumed 46% of energy. We talked with them back then. That is 3 years ago, I think. They batched the analytics to piggyback that on the when the file is being downloaded, and they actually reduced battery consumption by half, which is amazing. Second anti-pattern is multiple connections. Everybody is doing it, including myself, okay? We need to download several images from a website. We will open several HTTP connections, and we'll do multiple gets from that website. But here's another thing that I didn't tell you about till now. In cellular network, every TCP connection introduces some overhead because it needs to be encapsulated. So we're adding bits at the beginning and the end of the packets, which means that every TCP connection reduces the overall throughput that we have. If I have a radio channel, a cellular channel here that can give me 1 megabit per second, and I open 4 TCP connections at the same time, I'm not going to get 250K each. I will get less, around 200, 220K each. That means that we have lower throughput. The user needs to wait longer for the data. And it also means that we're spending more time in DCH or FSCH mode, meaning draining the battery. Third anti-pattern is duplicate content, basically downloading things that we already know, okay? First problem is when the app downloads something from the server and that something doesn't have any caching information, so the app can't cache it. Let's say the app downloaded an image, the image doesn't have caching information, the user sees that, exit the app, and 2 seconds later, he goes back to the app. We go back and download the same very image that we downloaded 2 seconds ago. Waste of time, waste of money, waste of battery. The solution is to use headers, the right headers like max age or expires when you send something to your client, and then the client can use it. Second problem is that content with caching information, the cache hasn't expired, but it is being downloaded anyway by the client. We've seen that happens a lot. So when we write some code that goes and fetches an image over the internet, we don't actually check if that content has expired or not. So the solution is simple. Don't do it, okay? I don't believe it. You're leaving me. Okay, friends. Anyway, third problem, content that has been downloaded, cached by the client. The cache expired, okay? But the actual file hasn't been changed on the server side. It's the same file. So usually what the client will do, it will go and say, hey, my local cache has expired, let's download that content again. But instead, the client can use an if modified since header. And then if the content hasn't changed on the server side, the server, instead of sending that image back, will send 304, not modified. And then the client knows that, hey, my local copy is still valid, I can use it. Instead of downloading a big chunk of image or whatever, we're downloading very small, only headers, only the HTTP header. last anti-pattern, connection management. So I know that most of us are using HTTP URL connection or OKHTTP or whatever, a library that gives us transport layer. But in some cases, we need to actually take care of connections ourselves to do some low-level operation in the socket level, if we're doing voice over IP or SIP or whatever. And we've seen several mistakes there. The common one is that we open a connection, we use it, and then we don't close it. We don't call socket.close because we think that, hey, the TCP will time out, and the TCP stack will close the connection for us. And actually, it does. But what happens is that in order to close the connection, we need to send TCP reset to the other side. And in order to send that TCP reset, we fire up the radio from idle to DCH to FSCH and back to idle. That's waste of energy, okay? Another common problem is that when we open a connection, just to have one ready for when we need it in the future. And then we fire up the radio just for the three-way handshake, SYN, ACK, and ACK. So if you do need to manage your connections yourself, open connections only when you need them, you use them as much as you want, you're done with them, please close them. So now that we've covered the common mistakes that a lot of people are doing, I want to talk about some advanced techniques that will help you to become better. And remember, our goals are less radio time and less data. Now, it's easy to say, it's a little bit harder to implement because when you think about it, in our app, we're dealing with many transactions. There are so many code paths that will lead to a transaction, to a thread that will fire up a network transaction. It's very hard for us as developers to say which transaction happens when and how to deal with it. So in order to make things a little bit easier, I decided what we're gonna do, we're gonna categorize network requests to 3 different buckets. First, there is the stuff that the user asks us now. The user clicks on the article and he wants to read that article. He wants to get into that specific post or whatever. We need data right now for the user. We need to go now and bring the data in order to display that to the user. Second type is those small data updates that we need to send to our servers when or while the application is running. Again, like analytics or location updates and whatnot. These are usually will be small payloads, and we care about them only when the app is actually running. The third type is when we want to send relatively big chunks of data to the server in order to sync. Let's say uploading a bunch of photos or doing email sync like Gmail does, or address booking, contact list sync like WhatsApp does. Okay? We don't really care about exactly when that transaction will happen. It's big chunks, and it usually happens in the background. Now, the second and third types we can optimize by batching. And the first one can be optimized by prefetching. And we're going to talk about these 2 techniques now. So let's start with batching. Batching, basically, we take a bunch of transactions that happens over time, and for every transaction, we actually pay a radio transition state, okay? Those transitions from DCH to FSCH to idle, I'm going to say that a lot today. And we batch them together. So we pay the overhead only once. Now, the easiest way to do that is by simply, when you have a network request, don't execute it immediately. Simply send it to a queue, okay? It can be a very simple queue or something more complex like, I don't know, content provider, or you can even serialize that transaction to persistent storage so you won't lose it if the app gets terminated. Now, you would ask yourself, when do I purge my queue? When do I actually go and send that? So an easy answer, let's say when we reach the threshold, let's say, I don't know, 10 transactions in the queue, let's batch them together and send them out. That works. But when we think about it, actually our phone is doing a lot of stuff in the system, and there is very good chance that another app will use the radio before the threshold is reached. So we would really like to get notified when somebody else is using the radio, The radio is always already hot. It's in DCH mode. Why don't we piggyback on that? It will be a very good idea for us to piggyback on that and transmit. And that's exactly why we introduced Job Scheduler in Lollipop. How many people here use Job Scheduler? Okay, you're in the right room. Good. So how do we do that? Basically, we specify job ID, the job that needs to be done, and some constraints like what network type do we want, and time. And actually, we can say, hey, some extra constraints. I want that transaction to happen only while we are charging. But Job Scheduler was introduced only in Lollipop. What happens if you're running on pre-L devices? So first thing that you can do is use Sync Manager and sync adapters. Sync adapters are great for those third type network requests, for those cases when you need to upload a bunch of stuff to the server or to sync data from your phone to the server, things that are not time critical and usually huge loads of data, big chunks of data. Okay? This is what Gmail is using to sync Gmail. This is what the address book is using. This is what WhatsApp is using. Basically, I can't think of an application that actually syncs something that's not using sync adapters. So sync adapters are great for the third type. But what happens with the second type? Those small data updates that occur while the app is running. Sync adapter is just wasn't built for it, and it introduced way too much overhead. For those, we have GCM Network Manager, which is very similar to Job Scheduler. Basically, let's say we want to schedule a task that will run from, I don't know, what's written there, from 5 minutes from now to 15 minutes from now. You specify the task, and you just need to override a single method when you inherit from a GCM task service, and you need to return either result successful, result failure, or result reschedule. If you want to debug when you're running with the GCM Network Manager, you need to somehow create that trigger to tell GCM Network Manager, hey, I want you to trigger that task. I want you to run it. And there is an ADB command for that. There are some caveats and limitations, so you better go to the documentation to read about it a little bit. But basically, it works, and it's great. Now let's talk about prefetching. If in batching, we wanted to grab a few transactions together and wait until we have enough and set them together, prefetching is all the other way around. Basically what happens, user opens the app, we fetch some data from the internet, the user looks at the data, he reads through it, in the meantime the radio goes back to idle, and then he clicks on something, and we go and we fetch some more data, the user sees it, and then he clicks on something, and we go and fetch some more data, and so on and so forth. Prefetching is all about predicting the future. Predicting what data we will need during this session, what data the user is likely to ask us to download for him, and actually download it now before he even asks for it. Think about it. We're not only improving battery life dramatically, we're actually improving user experience, because when the user actually clicks on something, the data is already there. He doesn't have to wait for it to be downloaded. First question, how much data do we prefetch? It's a tough one. So a quality prefetch we refer on a 3G network will be, I don't know, around between 1 to 2 megabits per second. On faster networks like 3.5 or 4G, we could go up to 5 megabits of data. But there's another way to look at it. Since it doesn't make any sense to prefetch data that the user doesn't want or that the user won't see, actually we can think of it from a different angle and say, hey, let's fetch enough data for the next minute or 2 minutes. Okay, that's usually the average session length in application, depends on the application category. So actually I really encourage you to go to analytics and look how much time users spends in session in your apps, and then you can optimize specifically for that time. So that's a good approach and algorithm, but we can improve it a little bit and be adaptive. Let's say we want to look at what the user is doing and what the device is doing. For For example, do we fetch more over Wi-Fi? Hell yes. Do we fetch more while charging? Of course, we download the internet while charging, I don't care. Fetch less while the user is walking? For sure. Because users, when they walk, their attention span to our app is lower. Average session type when walking is around 20-25 seconds, which is a good thing because if it was 2 minutes, like when we're standing, people will, get into parking cars or fall from cliffs or I don't know what will happen to them. Okay, fetch more when the user is driving? Depends. If your app is all about, I don't know, roadblocks and the hero moment of the app is while the user is driving, yes. If the user is driving, fetch more. And you can actually tell what the user is doing, if he's driving, if he's walking, if he's cycling, by using activity recognition API, which is in Google Play services. Do we fetch more over fast network? If we're on 2G, let's fetch less. If we're on 4G, let's fetch more, etc., etc. But we talked about adaptivity and how much to prefetch and how to change the amount of data that we prefetch. Now I want to ask you another question and take it a notch up. When to prefetch? What do you think? When to prefetch? When is the right time to prefetch? That's actually a question you can ask. When we're downloading data anyway. That's a good place to batch, actually. Prefetch is predicting the future. What? Login when the user opens the app? User logs in or user opens the app. That's a good place to prefetch, yeah? At night. At night, it's not a really good idea because if the user opens the app at noon, probably the data from the night is already obsolete. But we're going to talk about BG updates in a second. So actually, the right answer, the optimum point in time to prefetch is right before the user opens our app. Think about it. We save the user those 2 seconds from idle to DCH. He opens the app, and the data is already there. No need to download anything. No need to refresh. The app is fresh. The data is, right where it needs to be. The only problem with this approach is that our Crystal Ball API is still in beta, and we haven't released it yet. What? Yeah. So, but you can get to the early access. I'm just kidding. So instead, we need to take a different approach, and that's to do background updates. Similar to what you said, let's update at night, or when the user is not using the app, so when he will use the app, the data will be there. Now, background updates, the trick can be very, very tricky. And we need to ask ourselves what we update and how, in order to make that process efficient and effective. Efficient means that we don't want to poll the server and say, hey, is there something new? Is there something new? And actually drain the battery really, really quick. And effective, we don't want to fetch data that the user won't see. Okay? The whole thing here is to fetch data that the user will want to see, predict the future. So in order to understand what to update, I, again, segment the content to 3 different buckets. The first thing is the what's hot, okay? This is the data, the information that users are most interested in. This is why they have downloaded your app in the first place. If we're talking about a news app, that will be the top headline. If we're talking about sports app, that will be the current scores or live updates from the game, okay? This is the data that users care most. If you don't know what the data the user cares most in your app, A, it's a shame. B, go to analytics and take a look what users are doing, and then you will find out. The second bucket is that interesting stuff. This is stuff, it's not in the what's hot, but it's stuff that the user told us that he's interested in. For example, if we're talking about a news app, maybe we have a user that is very interested in the finance section, and another user who's very interested in the, I don't know, science section, okay, or political section. So the user actually told us hey, I'm interested in that information. It's not common, it's not for all the users, but specific users told that, hey, this is interesting for me. And then there is all the rest of this stuff. Now, when I look at background updates, I'm thinking of, all right, let's take a look how we update each piece of content. So for What's Hot, my server knows that something changed. There is no new headline, new results from the game, something new happened. The server can actually send us a GCM message with the data embedded in it. We can carry a payload of up to 4K, if I'm not mistaken, in every GCM message. And actually, our client, the app, can get this GCM message. We don't show anything to the user. We don't pop out notification, nothing. We take the data, and we store it in our internal database. When the user will open the app, all the WhatsApp is up to date. It doesn't need to wait every 1 single millisecond to see that. When it comes to interesting stuff, we can't use the same approach because we can't send everything to everyone all the time. We take a different approach. Basically, the server will tell the users via GCM that something has changed. Okay? Let's say something has changed in the finance section. All the users that said the finance section it's in their favorite list will get a message saying, hey, the app will get a message saying, hey, there is new data in the finance section. And then the app will use backoff to pull that data. And it will look, let's say, and now it can go in 2 different ways. Option A, we get this GCM message, something has changed, we wait a little, we go, we fetch the data, and then the user opens the app. Perfect. We predicted the future. Another way that this can go, it's in the other way around, okay? So we get a GCM, hey, something new, we fetch the data, and the user doesn't open the app. And then we get another GCM, something new happened, and we fetch the data, and then the user opens the app. Means that we've had a redundant update. We've wasted bandwidth, we've wasted energy. In that case, when we identify it, and it's very easy to identify in those cases, we basically increase our backoff exponentially until we reach to the right amount. So there are users that will open our app 4 times a day. There will be users that opens our app 2 times a day. We will pretty easy will find the right frequency to those background updates. And all the other stuff, we simply update that when the user opens the app. It's not really, it doesn't really matter. We can't really predict that the user will want that data. Okay. Third technique. We talked a lot about reducing radio time. Now let's talk about reducing payload size. Here's a test. There are 2 images on the screen. Who thinks the image on the right is higher quality? 2 people. Who think the image on the left is higher quality? 3 people. Who thinks I'm fooling you and that's the same image? Most of the people. Okay, thanks for the trust, guys. Okay, actually, one is 45K and the other one is 160K. A third. And no one here in this room could actually tell, hey, this one is better than that one. Okay? We can save a lot by compressing our images correctly. We don't need to go with 100% quality in JPEG. Actually, if you look at JPEG quality for the leading sites, Google, Facebook, Yahoo, etc., this is how the big guys are doing. Why don't you do the same? And since it is Big Android BBQ and Colt was supposed to be here, is not here, right? Colt? Good. So we can skip this slide. You don't need to go to see it. All right. Let's talk about Application Resource Optimizer, or ARO. ARO, it's a tool that was developed in AT&T several years back when I worked there. And I think about 2 years ago, we've open sourced it. What this tool does, it monitors all the network transactions and activity that we have that happens in our app, and it analyzes what the radio state would be for those transactions. It also runs a lot of tests against those anti-patterns that I've just showed you earlier today, and gives you an easy to digest report how you're doing. Okay? So give me one moment to arrange my screens here, and we'll be able to actually see it. Okay, so wait another second, and we can, this is gonna be challenging because I'm half blind, but it's all right. Okay, so I took an Israeli application, so no one will understand anything because the content doesn't really matter. And here we can see on the screen the report. And there are a bunch of tests that the tool did. And obviously green means good, red not that good, and you know that you need to fix those items, whether it's duplicate content or connection management or content not being zipped, stuff like that. But we can do some more with the tool. It's extremely hard to see from here. We have an overview tab, which basically tells us how much energy we consumed, how much energy was wasted on radio transitions, on signaling, etc., etc. But the most interesting part, at least for me, is this screen. Basically what we see here, these are the screenshots that I showed you earlier. We can see here the transactions. We can see here the transactions and actually the packets that were sent. And if we look into any single point of time, we will see on the right side the actual screen and what happened during that time. So during this splash screen, we can see here what packets have been, we've downloaded, what we sent, and we can immediately take a look and see that we were on DCH, went down to FACH, back to DCH, down. All that transaction, all those small transactions should have been batched into one single big one and save a lot of data and a lot of battery. Now let's take a look at this area. So the user clicked here on something, and he actually entered this article. This is a news application in Israel. Okay, again, you don't need to read what's happening there. Now I can see some transactions here, okay? And if we'll go down and look, we'll see that we actually downloaded the article and the images. But over there, there's another transaction. I don't see my pointer. I'm going to point anyway. Over here, there's another transaction, and I don't understand why it's there, okay? And obviously that, I think it should have been batched. So let's click on it. Where am I? Here am I. What changed? Did the user see anything different? The ad, exactly. So the user was actually reading the article. The radio went already to idle state, and just to change the ad at the bottom, we fired the radio from idle to DCH, FACH, and so on and so forth. We wasted a lot of energy. A better approach will say, hey, give me 5 ads, and then the client will rotate them without going to the network every time. So there's a lot in this tool. It's very hard to, in this setup, to actually go through over it, but I really encourage you to try it. It's called Application Resource Optimizer, ARO. You can find it on GitHub. You can compile it. There are zip file, APKs, everything. You will discover wonders on your app if you will use it. Yeah.
So if you've never done the battle bounding before, I can see running this tool having a bunch of problems right away. So
Yeah.
it seems like it would be easy to get overwhelmed. Is there a good place to start?
This is your best friend. Start here, see what you're green, see what you red, and all the reds, actually, if you click on them, you get some nice explanation. Hey, you're doing this, you're doing that, and even with, in some cases, not all of them, pointer to the actual packets that, you know, misbehaved, all right? And then you can actually, and in fact, if you only fix very few things in your code, you will see a tremendous improvement, just like get rid of all this periodic bursty traffic. And probably you have one process or maybe 2 that are doing that, okay? or improve prefetch, or let's do some batching. Let's do a transport layer that will batch some background requests, etc., and you're there. Okay. All right. So we do have some time left for Q&A. So feel free to ask whatever you want. Yeah. Actually, yes. Yeah, the question was, can I see when the radio is hot, or what's the state of the radio? Actually, the question is yes and no. You can see that in Android, you can't see it in your code. There is an ADB command. If I remember correctly, it's ADB dash B, and then space and radio. Check the documentation. You can tell ADB, you can tell the log cut from which buffer to present the logs. And there is a buffer for radio. And while you're running and your phone is connected to your computer, you can actually see in the log file of the radio what's the state, etc. So if you want that during debug to take a look, perfect. But while running and checking in your code what's the status of the radio, you don't have access to it. That's why you have GCM Network Manager and Job Scheduler that will do that for you. The question was, can I run this tool, Arrow, in a continuous integration and automated testing environment? Actually, I haven't tried that. So I don't really have an answer on that. There shouldn't be a reason why not to. The only problem that well, actually, when I think about it, okay. So Arrow, the way it works, you have data collector. First, you collect the data, and then you feed that data into the tool that I just showed you, which is basically the analyzer. Now, the data can be collected by using a specific APK, or you can actually feed it Wireshark dumps, TCP dumps, okay? So in your automatic testing environment, all you need to do is run TCP dump and dump those pickup files, and then in the morning feed them to the analyzer, and you immediately will see if there is a regression or not. Another one, yeah. Mm-hmm. Okay, so in cellular network, every TCP connection is actually encapsulated, which means that the cellular radio here and in the base station, they add bits at the beginning, at the end of that payload. So we actually add more bits that we need to transmit back and forth. Therefore, we reduce the overall throughput. The reason for that is that in cellular network, we often, I don't know what's the political way to do that, to say that, we often fake the TCP state, all right? So think of it this way. My phone opens HTTP GET request to, I don't know, to a server, or a TCP connection to a server, and I want to keep that TCP connection alive. That means that the phone needs to send TCP ACK messages back and forth. Now the cell network doesn't want those TCP ACKs. They don't add any value to the user. They're not actual payload. They just waste of frequency. And as I told you, frequency is extremely important to network operators. So what they do, actually behind the base station, somewhere at the base of the cell tower, there's a big machine that looks at all the TCP connections. And when that happens, when we open a connection, that machine will start talking with the server. And it will send those TCP ACKs on our behalf. So we can shut down the radio, we can stop allocating frequency to that cellular phone, but the TCP connection is still alive. And when that server will want to send something to the phone, he actually sends something to that big box that's there. It's called ASN gateway. And that box will then tell the base station, hey, we have data to that phone, give him frequency, and transmit the data to him. So basically, because we needed to do that, there is encapsulation for every TCP connection. Thus, we reduce the overall throughput when we are adding connections. Yeah. It's, yeah, the best practice is actually moving from HTTP 1.0 to HTTP 1.1, which uses persistent connection. So you open one connection and you run multiple GET requests on top of it. So I don't know what retrofit is using under the hood. I can tell you that OKHTTP is perfect. So OKHTTP actually use persistent connection by default unless the server doesn't support it, which is great. The only thing that you need to make sure is that you don't open several, or that you minimize the amount of HTTP connection, simultaneous connections that you open. Okay? Any more questions? All right, so I guess we're done here. Thank you.